Welcome, and thank you for taking the time to listen to Elise and I talk about Arkime today. Arkime is our open source, full packet capture system built on Elasticsearch. I started working on Arkime back in 2011 for AOL when I joined the security team, now known as the Paranoids. Elise joined the team in 2016. Her main focus has been on improving the UI, since what I did as a back-end developer wasn't necessarily the best. She also works on much of the middleware and adding new visualizations. So what is a full packet capture system? Well, you can think about it as a DVR for your network. Arkime monitors the traffic on the network. It will record the packets as they go by. It also parses them and saves the parsed metadata to Elasticsearch for the protocols it understands. Arkime should be deployed alongside your current security infrastructure. It doesn't replace your alerting software. It can horizontally scale to support hundreds of gigabits per second or even terabits per second, as long as you scale Elasticsearch with it. Arkime was created to replace commercial products that were just too expensive, saving us millions of dollars and giving us complete control of our deployment. We decided to open source it and to share with others what we had done. Arkime is usually used in an enterprise deployment, although you can use it at home if you want. The security team will have it monitor key network points, many times where the internal network connects to the internet. Arkime watches the traffic and sends the packets to disk and metadata to Elasticsearch. Your security team can then use Arkime when potentially bad things happen to review what is going on. We have been using Elasticsearch since 2011, back in the good old days. We tried out several other database systems at the time, and nothing really had the same feature set as Elasticsearch. It was also super easy to get started, and aggregations are amazing. We run huge clusters with petabytes of data, and one of the features we appreciate the most is not all that data needs to fit in memory. In fact, we only need about 1/100th of the amount of memory as we use for disk storage. Elasticsearch makes it easy to do so many cool things. Enough hearing about Arkime. Now Elise is going to give you a demo.
Now that Andy has told you a little bit about Arkime and how it works, I'm going to dive a little bit deeper and show you how an analyst might discover an anomaly on the network and investigate it using Arkime. First, they might start with this sessions page. Here, a user can see a list of sessions on the network. Arkime is sessions-based, unlike other systems like Wireshark, which are packet-based. We bundle all our metadata and all our packets into a session. This is just demo and test data. Our test data ranges from 1999 to now, so that's why you'll see a large range in our time range. And our demo data is just for the past few days. All this metadata that you see in our sessions table is stored in Elasticsearch. We store our PCAP on disk elsewhere. We're a lot like Kibana, but specialized for network sessions. We like to format our field values based on the field that they represent, and we like to group our fields in a logical way. A user might start here by clicking on the search bar and issuing a search. Arkime queries are mapped to Elasticsearch queries in our middleware. Andy will talk a little bit more about that later. We like to think that our query syntax is easy to use for an analyst. We have over 200 unique fields that a user can search for and view. So we like to provide a nice type ahead for a user to find the field that they're looking for. So here, I'm looking for a field that's a file name for an email, and I want to see if there are any file names in emails that exist on our network. We have one and our test data suite. This is the field that I was looking for, and here's the value. You can open up any session to view its metadata. As I said, all this metadata is stored in Elasticsearch and easily searchable. We like to group our fields logically. The top section is metadata for all network sessions. As you scroll down, you'll see more specific data for each type of session. For instance, this is an email session. If you scroll down even further, you can see the packets for this particular session. You can view them in different formats. You can toggle on the source or the destination packet visibility. I'm going to show both here for this demo. On the left, you'll see all the source packets, and on the right, you'll see all the destination. If you click the Show Packets button, you can see the packet flow. For instance, you can see the SYN-SYNAC exchange. You can also view it in the default view, which is reassembled packets. If you click our Show Images and Files button, you can view any images that were in this email or any files that were transferred within. If you scroll down, you can see there's that a.zip file. We could download this as an analyst and use other tools to investigate it and determine maybe if this was a bad email attachment that a user downloaded and affected our network. As you might have noticed, and I referenced earlier, at the top you will see our timeline view. I'm going to clear the search so that we can see the timeline view for all our data. We have a bunch of test data that is not very interesting, so I'm going to narrow in on our demo data. Our timeline view is a pretty good way for an analyst to view what's happening on the network during what time. We are populating this particular view by running an Elasticsearch aggregation query. Aggregation queries are one of the main reasons why we wanted to use Elasticsearch. It provides us with the ability to allow a user to see a lot of awesome data in a different way. Rather than just a list of sessions like in the sessions table, this is a list of sessions over time. So a user might be able to see this anomaly. There's clearly an issue going on in our network, so let's narrow in on this time range. So generally, we see we have between 11 and 7 sessions per second. However, here we're seeing a spike. There's 132 sessions right here. So an analyst might want to decide how to investigate this issue and whether it's something that's bad on our network. To do so, they might want to switch to a different view. As I said earlier, this is just a list of sessions. They're not going to want to open every session and compare one to the other to find anomalies. They're going to want to have a different view of this data. So they might switch over to our SPY view page. This page displays another Elasticsearch aggregation query. It displays unique field values and their counts. So if we look down in our general area and look at this destination IP, it clearly has the largest number of sessions reaching out to this destination IP. So this might be our anomaly. Like I said before, we group our fields logically. So let's scroll down and see that all of these sessions are HTTP sessions. So let's open this section and maybe turn on some other fields. Let's turn on the path and a user field. And we can see this file is being downloaded more than any other file. All these others are just one. This one has 327 instances. Also, this user, me, Elise, I'm creating a majority of this traffic. So my computer, might have some issues. So now that we've determined where this issue might reside, let's look at another view of the data. This is our SPY graph page. It lists, just like the SPY view page, unique fields and their counts. So we can see the source IP, there's nothing really going on here. Let's look at that destination IP field that we determined was bad earlier. Here you can see, indeed, this is where the spike occurs. It is from this destination IP. This view is pretty awesome because it shows you not just when something happened, but also where it happened on this map. Another view you might use to look at this data in a different way is a donut graph. Here you can see, yep, same data. That destination IP is a bulk of the sessions. One thing unique about the donut graph as opposed to the timeline graph is we can add more fields and layer them. So we can add the user. So we can see Elise was the main user reaching out to that destination IP. However, Sadia also connected to that IP. So maybe she was also part of this, or maybe her computer was owned. We also noted that the URI path was something that was causing this anomaly. And here it starts to get a little bit complex. So I like to open up the table view. Here you can see a table. It has the same data as the pie graph, but you can sort the fields. So maybe the analyst might want to figure out, is anyone else downloading that crisis.php file? In which case, they can sort by this value, scroll down and see, okay, there's only one. Sadia did not reach out to that IP to get this file. So likely her computer wasn't owned. It was just Elise. It was just me. I'm the one that reached out to that IP so many times and requested this particular file. Now that an analyst has started to diagnose this problem and figure out what's going on, they might want to create a unique view so that they can further analyze this issue. So I'm going to add that path and that user to the search bar. I can then create a new view I'll name it, I'll create it, and now behind the scenes, without typing anything into the search bar, I can apply this view to any query and make more analysis. Let's head back over to the sessions page. So now this particular query is applied. I don't have to type anything into the search bar. So now I'm only seeing the sessions from Elise's computer where this file was downloaded. So this allows the user to create a unique view so that they can easily keep analyzing this. Maybe they're going to dive into more sessions and try and figure out what this file was, why this spike happened, and what it's doing to our network. As you can see, Arkime is a powerful tool because Elasticsearch provides fast searching and aggregations. Andy will explain more about Arkime queries and how we map those to Elasticsearch queries and aggregations, as well as how we scale Elasticsearch and break some of its rules.
For the great demo, Elise. Arkime provides an easy-to-use expression language. We found the Lucene string syntax very complex for new users, so we created our own DSL. Information about Arkime's fields is stored in Elasticsearch. We store the type, field category, help text, and how to display each field, for example. This information allows us to be smart when converting Arkime queries into Elasticsearch JSON queries. It also means that new fields and how to display them can be automatically added without even restarting the UI. We also support special fields where a single Arkime expression might search across multiple fields. So in this example, if you search for IP equals 1234, it will convert it to an Elasticsearch query against all IP fields. The Elasticsearch aggregations are super expressive and allow us to generate great visualizations. We use them all over Arkime, from our timelines to our maps to powering most of our tabs. If you aren't using them in your app yet, definitely take advantage of them. The one aggregation that is still missing is IP bucketing by subnets. Hopefully we will see that be added this year. Arkime produces a large amount of data. I mean a lot of data, multiple petabytes of data. We use large machines to store this data, and we have a large number of machines. To support a high amount of indexing, we use a hot-warm architecture with SSD-based hot nodes for our busiest clusters. We move the indices off of our hot nodes after a few hours. We've also found that even with large machines, it is still best to only run one Elasticsearch node per machine. While you can run multiple nodes, we've had problems with replication and shard awareness, where multiple nodes on a single machine can overload the machine's resources. If you run clusters with enough nodes, maybe 8 or more, definitely look at shard awareness features, sometimes called blue-green or even odd architecture. Elasticsearch allows you to assign an attribute to each Elasticsearch node. By using 2 different values across all nodes and replication of 1, Elasticsearch will place the shards appropriately. This means for maintenance you can work on a large number of nodes, half if you want to, and take those out of rotation and never go red. Because we run such large clusters, we break a few Elasticsearch tenets. While not recommended by Elastic, it might even invalidate any support contract, we've had mostly excellent luck. Here are the 3 that we've broken. Heap size. You'll read everywhere about the magic approximately 30 gig limit on heap size, and how you'll actually use more memory and go slower if you use more than that. While it is true if you go above the 30 gigabytes, just a little, you'll use more memory. However, if you go way above it, it's no longer true. This is the same issue many of us experience porting 32-bit apps to 64-bit apps. We actually use data nodes with greater than 48 gigabytes of heap without an issue. The same goes for disk usage. The common wisdom we've seen is 8 terabytes max. Again, we push the limit by going over 20 terabytes and even 30 terabytes in some cases. While you might not want to use this kind of deployment for a real-time system powering a consumer website, for Arkime and other log-type deployments, it works fine. Finally, let's talk about cluster size. Even with large machines, storing petabytes of replicated data can still require a large number of nodes. Elastic recommends using smaller clusters and cross-cluster search. Currently with Arkime, we don't support that deployment, so we've been using large 100-plus node clusters for a while. We found the only downside is that you need more heap space for all of the state being sent around. We found that breaking these 3 rules allows us to have large clusters with no issues at minimal cost. Now there are a few recommendations from Elastic that you should follow. We attempted to not listen to these, and it bit us. First and foremost, definitely try and keep your shard and index counts as low as possible. This goes a long way to preventing many Elasticsearch issues. This goes for whatever kind of application you're building, whether a consumer or a log application. Arkime by default will try and guess good settings for your cluster, but it allows you to override them. Next are the recovery settings. While attempting to change, they should mostly be left alone. With shard awareness, it is possible to get into a state where the shards are constantly shuffled with no end in sight. The one exception to this is the recovery speed settings, which you should raise, but only after thorough testing. In general, the Elasticsearch defaults are usually pretty good for most settings. Lastly, do spend some time testing your sizing and cluster speed. Elastic has tools to do this, or you can always just test in production. For Arkime, we provide an estimator for how to size your cluster based on your network throughput and other input. However, many times the numbers you get from your network team are off. We find it best to actually make sure you have a two-phase budget when deploying Arkime and Elasticsearch. The first phase is based on what the network team tells you and the Elasticsearch estimator tells you. The second phase is truing up your deployment based on what real life actually looks like. Arkime is an open source project. We would love to have people join us in our journey to make Arkime better. We are very transparent and use Slack and GitHub for everything, and would love to have more contributors, no matter your interest or skill set. We have open office hours every few weeks where you can ask questions and see demos of what we are working on. We hope to see you there. Hopefully today you've learned how you can use Arkime and what full packet capture is. Building simple visualizations in Arkime wouldn't be possible without Elasticsearch's awesome aggregation features. We would love it if you join our open source efforts in building a great tool. Thank you very much for your time today.